Building a global system for 1 billion active users requires managing a truly staggering volume of concurrent internet traffic. While sending an email seems deceptively simple, it involves one of the most storage-heavy distributed systems in modern computing. For our design, the scale is explicit. We must support 1 billion users, which translates to a consistent load of over 100,000 requests every second. These telemetry numbers show the actual storage footprint. We are looking at 730 petabytes for metadata alone, and over 1.4 exabytes required to store attachments for a single year. We are also forced to route this massive volume through protocols invented in the 1960s, like SMTP, POP, and IMAP. Traditionally, legacy mail servers handled this by writing directly to local file directories, a structure known as maildir. In that model, when an email arrives, the server processes it by writing the message directly to a single local disk. That works for small volumes, but when a legacy server attempts to process hundreds of thousands of concurrent disk operations, it inevitably flatlines. The bottleneck is physical. Disk input-output operations per second will instantly paralyze a synchronous single-node system. Surviving this volume requires completely decoupling operations, optimizing custom NoSQL databases, and building massive infrastructure dedicated to proving the system's legitimacy to the rest of the internet. Our architecture starts at the edge, where webmail clients connect to the system via a central load balancer. This load balancer feeds requests into a cluster of stateless web servers through RESTful APIs. Crucially, web servers only manage API requests. They never process SMTP directly. When an email enters, the server immediately separates the payload into two streams based on size. Heavy payloads route directly into an external object store, like Amazon S3. Storing massive encoded PDFs in a message queue creates an immediate performance bottleneck. By isolating heavy files, lightweight metadata drops into a dedicated outgoing queue, preventing web server blocking. Background workers then pull from this queue and interface with the internet to complete delivery. The receiving flow reverses this logic to prevent traffic spikes. Incoming messages bypass web servers, hitting the load balancer and routing directly into an incoming queue. Workers pull from this queue when virus checks, save to storage, and push live updates via WebSockets. This aggressive queue-based decoupling provides the necessary shock absorption to protect the front end from massive payloads and unpredictable traffic surges. Below the routing layer, we have to design a storage system for metadata. Email metadata is paradoxical. It requires completely isolated access for individual users, but the read operations are highly sequential, focusing on the most recent messages. Traditional relational databases and blob storage fail here, struggling to handle write-heavy patterns and sequential reads at this scale. To guarantee performance, we group a single user's data onto one physical node, using the user ID as the partition key. This strategy forces a trade-off. For each mailbox, we must prioritize strong consistency over high availability. If a primary node fails, we pause sync operations for that specific user, rather than risking split-brain data corruption or lost messages. This consistency enables conversation threading, a graph traversal based on client-generated data, specifically the message ID and in-reply-to headers. Reliable delivery and accurate threading both rely on these specific headers being stored in a highly consistent, write-optimized NoSQL partition. Building an email search engine is the exact opposite of the web. Web search is massively read-heavy against a static index. Email search is violently write-heavy. Every received message triggers an update, even when read requests are nearly non-existent. This write-heavy load persists despite the fact that most users rarely search their inboxes. Handling this continuous background load requires an asynchronous indexing pipeline, where workers push event data into a Kafka stream. Relational database queries are simply too slow to parse unstructured text at this volume. We use a log-structured merge tree, which optimizes for continuous, sequential disk writes to keep the index updated in near real time. Scaling email search means moving away from relational queries and toward a custom, write-optimized indexing pipeline. The final hurdle is getting the internet to accept our messages. This reputation dashboard shows a typical 6-week curve for warming up new IP addresses. Sending millions of emails from a new IP on day one will cause internet service providers to permanently block the system.
Deliverability requires dedicated IP pools to strictly separate transactional messages from bulk marketing. We need a specialized feedback loop to process the error messages and rejections returning from external providers. The system automatically sorts this incoming telemetry into 3 distinct queues for soft bounces, hard bounces, and complaints to maintain the sender's reputation. Beyond behavior, the system must use cryptographic verification to prevent domain spoofing. Protocols like SPF, DKIM, and DMARC verify that an email originated from an authorized server. Sending email at scale is a continuous, automated cryptographic negotiation to mathematically prove the system's legitimacy. Ultimately, all of these complex software layers eventually have to run on physical hardware, operating together at a massive global scale. Pulling back, we see the architecture deployed across several geographically isolated data centers. True reliability requires replicating the metadata and object stores across these different regions. If a network partition severs a major transatlantic connection, the system must remain resilient. Local routing seamlessly redirects users to the nearest healthy data center, serving cached and replicated data from surviving regional hubs. This multi-region setup provides horizontal scalability and ensures that users never experience a total outage during localized failures. Operating a billion-user inbox requires maintaining the balance between aggressive asynchronous decoupling, right-optimized data modeling, and relentless cryptographic reputation management.